Everyone, in this video I'll cover some properties of tensors which will be used many times in general relativity, so it's necessary to know them beforehand, and I'll also solve a few problems related to it. Let me write the definition of contravariant tensor. A prime of mu is equal to del x prime mu upon del x nu a nu. This is our contravariant tensor. The components of contravariant tensor are denoted by upper index like this. We have covariant tensor denoted by lower index like a prime of mu is equal to del x nu upon del x prime mu a nu. This is our covariant tensor. Now I think I forgot to mention this in the last video, but scalar is also a rank 0 tensor. It doesn't have any indices, and when we go from one coordinate system to another, it remains invariant. So when we go from S frame to S prime frame, if A is a scalar, it just goes to A prime, which is equal to A again. So it remains invariant under the coordinate transformation. Now let's come to the first property of tensors called linear combination. So if we have linear combination of tensors with same lower and upper indices, then the resulting quantity is also a tensor. What I mean is, if we have, let's say, C times AB plus D times BAB, where C and D are scalars, then this resulting quantity is also a tensor with same upper indices TAB. To see how this is a tensor, let's write the transformation equation. T prime AB will be equal to C A prime AB plus D B prime AB. The C and D are transforming to the same quantities because they are scalars. Now we have, by contravariant tensor transformation of this tensor, we have del x prime A upon del x P, del x prime B upon del x Q, A P Q, since A transforms contravariantly with respect to these two upper indices. And similarly, we have D times del x prime A upon del x P, del x prime B upon del x Q, B P Q. I'm using the same dummy indices P and Q over here because then we can take this factor common, del x prime A upon del x P, del x prime B upon del x Q, and we have C APQ plus D BPQ. Now you can see that this quantity is nothing but TPQ by our definition. So T prime AB is equal to del x prime A upon del x P, del x prime B upon del x Q, TPQ. Now if you see how this is transforming, we can conclude that TAB is indeed a rank 2 contravariant tensor. So we proved that the linear combination of two tensors having same upper and lower indices is also a tensor. Now let's move on to the next property. It is the direct product between two tensors. So if we have product of components of two tensors like A alpha, B, or I'll use C, beta, gamma, if this is a tensor, and this C beta gamma is also a tensor, then this direct product between their components also gives out tensor with the upper and lower indices like this, T alpha beta gamma. So it will have the upper lower indices of the original product. Now to prove that this is a tensor, we'll use a similar procedure. So we have T prime alpha beta gamma is equal to A prime alpha C prime beta gamma, and we have been given that these two are tensors. This is a covariant rank 1 tensor and C beta gamma is contravariant rank 2 tensor. So we'll write transformation equation for them. So A prime of alpha will be del x p upon del x prime alpha AP, transforming covariantly with respect to alpha, and C prime beta gamma will be del x prime beta upon del x q, del x prime gamma upon del x r C q r, transforming contravariantly with respect to beta and gamma here. So we'll take these factors together and we'll write del x p upon del x prime alpha, del x prime beta upon del x q, del x prime gamma. So I think I've written gamma twice here. Sorry, this is r. One of them is gamma, so this is gamma. I'll use another index s so that I don't confuse it with gamma. So here I have del x prime gamma upon del x s and AP CQS. So this is what we have, and on the left hand side this was nothing but T prime beta gamma and alpha. Now this quantity over here is same as TP QS by our definition. So we have T prime beta gamma alpha is equal to del x p upon del x prime alpha, del x prime beta upon del x q, del x prime gamma upon del x s, T, q, s and p in the lower. So from here you can see that T alpha beta gamma indeed transforms like a tensor. So T beta gamma being a direct product of A alpha and C beta gamma also transforms like a tensor. So this was about the direct product. Now the third property or third procedure with tensors is contraction of a lower and upper index. So when we set a lower and upper index in a tensor to be equal so that we sum over it by Einstein notation, this will give us another tensor whose rank is 2 lower than the original one. Let's see what I mean by this. So if we have a mixed tensor ABCD, and if I set C equal to B in this, so if I have TAB BD, this is called contraction of an upper index and a lower index, and this will be a tensor, a mixed tensor of the form TAB. The rank of this is 2, and this is, we originally started with a 4 rank tensor. So this contraction of one upper index with lower index gives us a tensor whose rank is 2 lower than the original one. So I'll just write it rank 4 and this is rank 2. To see how this is a tensor, this is a rank 2 tensor, we'll take T prime AB BD, the contracted indices, and by tensor transformation, like I have shown in the previous video, we used a similar tensor there. So this will just give us del x prime A upon del x P, del x prime B upon del x Q, transforming contravariantly with respect to AB and covariantly with respect to BD, which I'll write as del x R upon del x prime B, del x S upon del x prime D, and we have T PQ RS. I'll just write this more properly. So we have del x S upon del x prime D and T PQ RS. So here look at these two terms. Here del x prime B and del x prime B is common, so we can write this as del x prime A upon del x P, del x R upon del x Q. These cancel out and we have this, and then del x S upon del x prime D, this term, and T PQ RS. Now focus on this term over here. When R is equal to Q, then only this will give us 1. Otherwise, when R is not equal to Q, this will give us 0 because our space-time coordinates are independent. Ct, x, y, z are independent coordinates. So derivative of one of them with respect to the other will be 0. So here what we have, this is just Kronecker delta RQ. This by definition is 1 when R is equal to Q and 0 otherwise. So we have del x prime A upon del x P, Kronecker delta RQ, del x S upon del x prime D, T PQ RS. And here we have T prime AB BD. Okay, now multiplying this with this will give us TPQ QS, because if R is not equal to Q, then this whole term will be 0. So the product of these two circle terms will be del x prime A upon del x P, del x S upon del x prime D. So the product of them will be T PQ QS. Since this B is summed over, I can write this as T prime AD like I defined before, and this is equal to del x prime A upon del x P, del x S upon del x prime D, and here Q is contracted, so it is TPS. So you can clearly see that TAD is indeed transforming like a mix rank 2 tensor, where it's transforming contravariantly with respect to A and covariantly with respect to B. Clearly seen from this equation I've written in the box. So this just goes on to show that when we contract one lower and upper index, the resultant value is a tensor having rank whose rank is 2 less than the original one, like I showed you. A result of this contraction is that if we have a quantity A alpha, then this is a scalar, because A alpha is rank 1 contravariant tensor and this A alpha is rank 1 covariant tensor, and we are contracting this index alpha. So the resultant tensor will be a scalar that is rank 0 tensor. To see this explicitly, let's just take S prime is equal to A prime alpha. I'll erase these. This will be equal to del x prime alpha upon, let's see, del x, what should I call this? It's P, okay. AP, this is a contravariant tensor, A prime alpha. This A prime alpha is a covariant tensor, So I'll write this as del x q upon del x prime alpha aq. Now taking product of this with this del x prime alpha will go away, and we'll have del x q upon del x p ap aq. Now as seen previously, this is nothing but Kronecker delta qp ap aq, and this product just gives us ap ap. And this is nothing but our s that we started with, so we get s prime is equal to s, and this just proves a alpha is a tensor, is a scalar, that is rank 0 tensor, that is rank 0 tensor. You can also think of this quantity over here as direct product between two tensors, so the resultant quantity is a tensor, and we have these two indices contracted, so the resultant will be a scalar rank 0 tensor. In the upcoming video, I'll solve a few more problems on tensors which will involve similar manipulations like we have done here, and they will show clearly how to solve tensor algebra problems. They will be used many times. The results we are proving will be used many times in GR, and we will need to refer back to them. And if you know tensor algebra properly, you can just see what is happening in the equations of GR more easily than otherwise. So yeah, thank you for watching, everyone.